session, and yeah, so speaker is very real Bary-Soroker, and his talk title is Past and Present of Probabilistic Galois. So thank you.
Thank you.
Please, yeah.
Hi everyone. I remember the first time that I was here. I was very impressed that all the people wore jackets. So I especially bought a jacket because now I'm the old guy, but it's too long, so excuse me. Okay. So I want to talk about the probabilistic Galois theory, and I want to give some overview. It's a topic that is studied from a different point of view in recent years. Some of them we heard in the talk of Craig Westerland. I will take a different point of view, and I have some goals for this talk. I want to present the setting that I will be interested about and describe some of the different models that get attention in recent years. And there was really interesting progress on all kind of directions, so I want to present some of the results that I find nice and maybe state some challenges that are ahead. Okay? And to finish on time. I forgot to write it. So the basic setting is we have a polynomial, f of x, and I think of the coefficient as random variable, not necessarily identical, not necessarily independent. It depends on the model how I will choose them. There are some natural ways to choose them. So f of x is a random object, is a random polynomial, and I will always assume that the coefficient take integral values almost surely, so it's a random polynomial over the integers, and I have its Galois group GF, which is the Galois group of the splitting field, and at least if the polynomial is separable, it's a well-defined subgroup of the symmetric group, and this is a random group of the symmetric groups. And I will be interested in two main questions that I will write. So you will remember them. Question number one is how f factor, what is the distribution of the factorization, but let me write it in a more naive way, is f irreducible with a high probability. Of course, it depends on the model, and in the model I will always have at least one parameter that grows, so it will be a asymptotic question. And the second question is how the random variable GF distributes. So, for example, is GF equal Sn with high probability? So I think today we had a talk in which the polynomials never had Galois group Sn. So if you will take model of composition of polynomials, this question is less relevant. This is why I stated the general question. And I want to talk a bit about motivation. One of the practical motivation for this study is that it produced new tools in Galois theory. There are two basic questions: the inverse Galois problem, which is interesting because we don't know how to solve it, but it's not so interesting for application. And there is the direct Galois problem. Given some polynomial or geometric object like monodromy group or representation, Galois representation, can we compute the Galois group, or can we say that it's large, or can we say something on the Galois group? And the direct Galois, I call it the direct Galois problem just because it's the opposite of inverse. And the direct Galois problem is really important in application all over algebra and number theory and probably beyond. So it's nice that these kind of questions that are naive in a sense, produce new tools for the important question in some sense. And also this question gives some insights to the inverse Galois problem, but mostly it gives some kind of explanation why it's so difficult. Because some probabilities are really small, at least expected to be small. And there are some, I don't know if it's hidden beauties because they appear in the internet. Those polynomials are really interesting. So what you see here, it's a illustration of some Derbyshire. And he took all polynomials with ±1 coefficients up to, I don't remember, degree, maybe 17. I don't remember exactly which degree, up to some high degree, and he put them on the complex plane. This is what you see upstairs. Okay, and you see beautiful, and if it's very bright, it means that there are many polynomials there, so many zeros. So you just drew the zeros. And you don't see it because maybe you will see it if you look here. There is a line on the real axis. There are about, if you see, there are about log n polynomial, log n zeros, real zeros for each polynomial on average. This is something that that was studied by Ofer Littlewood, how many real zeros there are, and it's about constant times log n. You see the holes. The holes are, it's a bit cheating because the holes are around the roots of unity, and for example, one is very probable. So one appears with high frequency. Therefore, in order that it will be equidistributed, there is some kind of how do you say, repulsion. Repulsion, yeah. So these are the roots of unities. Because roots of unity appear with very high multiplicity, it looks like there is a hole, but inside the hole there is a point, very bright point that we don't see because of the resolution. And these are a magnification of some of the nice, just to see the fractal nature of this. It's a really beautiful from I don't know, naive point of view. So this is why people are studying random polynomials for many years. So let me start to, yes.
What is the other picture?
These are just magnification of the same picture of different areas. Between us, once I applied to a grant, and I thought that it would be nice to magnify them.
Yeah.
Some is very nice, and it gives you a high resolution picture. So you can magnify as much as you want. So thank you, Sam. So very briefly, the models that that people are interested in is maybe from number theory, the independent coefficient models are the most natural, where at least if the measures are uniform, this is really counting questions. And I will elaborate on these two models the most, but there are other models where the coefficients are not independent, but are still very natural. For example, characteristic polynomials of some metrics in some ensemble, either if you're, depends where you come from, which ensemble you take. Entries should be ±1. I don't know why it was deleted. But okay, and there are all kind of other models that were of some interest, like additive polynomials over finite fields, polynomial over local fields, where Roy here is working, Roy Shmueli is working a lot about, but other people too, and maybe I will say a few words about this, reciprocal polynomials. And as we saw in the talk of Craig Westerland, if you count by discriminant, it's not by polynomials, because when you count with polynomials, there is multiplicities. This different polynomial can give the same number, of course. So there is a lot of research on that, but this will not be the direction of this talk. I used a little bit AI for this presentation. And it says that I need to go to the blackboard. So what can you do? So I need to stop sharing, right? And to leave the meeting, but only virtually. So let me start and talk about on the large box model. So in this model, I take the polynomial f of x uniform with the psi I between some minus h to h, and let's say that they are uniform plus independent. So this is really a counting question.
N is fixed.
What?
N is fixed.
Just and I will say it in a second. So this is the model, and the important thing, as Ron just said, h will go to infinity in this model. So you see, I choose it from, if you think about the coefficient, it's from a box. And what does it mean that it's a large box? It means that the size of the box is much larger than n. I will actually discuss a little bit what it means much larger, but for the first approximation, let's say that it's fixed. And here, this kind of model is very famous in number theory, and it goes back at least to answer 1. So in this model, we know at least from van der Waals, maybe even from Hilbert, that yes, almost all polynomials. This is a derivation for almost surely. When I say almost surely, I mean that the probability 10 to 1 as the parameter goes to infinity. Okay. So yes, almost surely the probability f is irreducible. Moreover, I think it was Chela, he proved that the probability that f is irreducible equals 1 plus or maybe minus Cn over h plus O of 1 over h squared. And this the implied constant here depends on n. And this is an explicit constant. This is just the probability that f has a 0. So it's in Z. So it's not difficult to compute this probability. Okay, so it's very explicit, but here the constant depends on n, and in not such a nice way. If you want something more elementary, and this is just in case you want also that n will go, because we don't like polynomials of degree only 10. We want it to grow more and more. So more elementary, you get that the probability that f is irreducible equal 1 minus O of, let's say, n over n log h over h. So it's less optimal, but this implies constant is absolute in the sense that I don't remember exactly how much it is, but probably if you put 100, it's good enough. So it's not optimal in h, but at least the dependence in n is not bad. Okay? So this is about question number 1. Question number 2 goes, the answer goes to van der Waals and maybe even before that to Hilbert. And the answer is still yes. How does G distribute? See the second answer, yes. So the probability that GF is Sn is 1 plus small o of 1. This is a result of, say, Hilbert or van der Waals. Now, van der Waals gave an explicit error term. And so this goes to 36, if I remember correctly, 1936. Will not be published in 10 years, but And if you want more exact error terms, because you want to see the dependence in n, then maybe this is the nicest that is uniform in all parameters. So this is Gallagher in 73. So it's 1 plus capital O of, let's say, NQ n to the 3 times h to the minus half plus epsilon. So, and this epsilon is explicit, some power of law. So it tells you that at least if h is bigger than n to the 7th, for example, then it still goes to 1. So you can let n grow. Most maybe n is fixed, but in our gut we want n to grow too. And if you want to optimize on h, I mean, we know from this result, we know that we cannot go below 1 over h, because the probability to be reducible is 1 over h, and then the Galois group is not Sn. So here we have a line of results. Let me give you some names. It's not all the results, but these are some central result in the study. So Dittmann, but not Dittmann. Arnaud told me that there is a difference in the pronunciation, but not now, okay? So Dittmann in 2011 improved on Gallagher, and then there was something very, very interesting that I saw in mathematics a few times, but in this story it was extremely interesting. In 2021, there were 3 improvements, three substantial improvement of this result from 2011. So maybe I'll write what it is. It's the error term was h square root of 2 minus 2 plus epsilon, which if you think about it, it's better. I need to do it in my head, but so in 2021 there were a bunch of results. I wrote the names because the first result was one of this project that a group of people worked. So first it was Anderson. This is a paper by Anderson, Gaffney, Lemke, Oliver. It's a nice result, even though Laurie. So I bother writing their names because it's a lot of names. Shanka and Zhang. So this was one result in 2011, and then immediately after there was the result of Cho and Dittmann. And finally this was the last result, but it's by far the best. So I will only state this, but by Bargava. So what is the last result? It says that the probability that GF is not Sn comes from only 2 options. So one option is that the probability of F having a root, which we understand very well. It's very easy to compute. It's some explicit constant divided by h, plus the probability that the Galois group is An, plus an error term of 1 over h squared, depending on n. We know that this is 1 over h, and in fact, he also proved that this is O of 1 over h. And this was substantial, but this part, I mean, with different error term was also done by Cho and Dittmann, but the big achievement was to show that this probability is smaller than 1 over h. Some remarks that are interesting. So the first, you remember I told you that van der Waals was the first to prove it. So van der Waals asked, what is the second most probable group? And in fact, he didn't ask, he conjecture. A conjecture that it is Sn minus 1. So this is the same as GF is in Sn minus 1. So van der Waals conjecture that the error term, the second was if you pick a polynomial and it's not with Galois group Sn, it's very rare. But if it's not, van der Waals conjecture that almost surely you will get Sn minus 1. And this is from 36, and it took almost 100 years to get that the second most probable group is either Sn minus 1 or An. And we still don't know which appears more frequently, but at least we know that this doesn't appear up to a constant faster than this. So Bar-Gava solved a weak version of this conjecture. So, and again, it took almost 100 years of many tries to get there. So it's a really impressive result. A second remark is that, it's like in results in number theory, someone proves some big result, but it's so far from what we want to know. So second remark is that the probability that GF equal AN shouldn't be 1 over H. I don't know, what do you think? I take polynomial of degree 10, say. I take polynomial of degree 10, let's say, and height, I don't know, 1,000. So what is the probability that it's that if I pick it's so how many, in other words, how many times do I need to pick a random polynomial to get AN? So if this was the correct answer, I would need to pick it 1,000 times. But it's very difficult to do numerics here, even for n equal 5. But maybe this is something like, I write like this because I don't want to get to all kind of log factors, h to the minus n over 2. Which is in this case, how much is it? It's 0. How much is h to the 1,000 to the minus 5? It's roughly 0, I think. One, two, three, 4, 5, right? So it would take a lot of, if you are just dumb, then you just tell the computer, choose the coefficient randomly between minus 1,000, oh, well, this is between 1 to 1,000. Choose them, then you will never get AN. So you need to be smarter. A third remark, we have some lower bound. So I'm really thinking that this is the main challenge in the large box model to understand this. The best result, which is very good and very strong with a lot of interesting tools, is by Bar-Gava. Lower bounds. So what do we know? We know that the probability GF equals AN is bigger. This is up to a constant that depends on n, bigger than h to the minus n over 4. So it's not really this, but still it's a lower bound. Before this, people thought that it would be 1 over h because, okay, I want to do other models, so I will not get. And this is a result of myself with a student Ben Forat and with Vlad Matai, the postdoc, and now he's in Romania. The point is that we found a really nice symmetry of polynomials. Let's say if n equals 4 if n equal 0 mod 4, then if you restrict yourself to polynomials like this, polynomial f such that the f plus f prime is a square, you can show that almost surely they will always have Galois group inside an an, and almost surely it will be an. And we were very happy, but with experience, I know that if I find something simple, some simple symmetry, it should be known. But it was really surprising that we found a paper of Hilbert that had not exactly this symmetry, but a very funny symmetry, very similar symmetry. And Hilbert said that he learned it from Hurwitz. So even Hilbert was not. So there are symmetries for discriminant. And last remark is that if you're just interested in a square discriminant, then somehow you can find a better family, but so it's something like h to the n minus 2 minus a half plus epsilon. But here, never an. So it's always a smaller group. If you want, it's something like polynomial which only have even terms. Okay? And the free term is a square. So if a polynomial has only even terms and the free coefficient is a square, you can show that the Galois group is that the discriminant is a square, and then but the Galois group there are more symmetries because the roots comes in pair. So the Galois group is not primitive. So and this is also by those guys. Yeah, so this was quite 2021 was quite an exciting year. Everything was boiling, and at the end we actually got the van der Waals conjecture, or a weak version, but extremely. I mean, this is what people try to get to this thing. I mean, of course, you want more, but he really achieved what we hoped to achieve. Good. So let me go to a different model. Let me go to the restricted coefficient model. So I started at 420, right? No, okay. So to be a bit quick, let me not give you the full picture, just one case that I find the most interesting and I show you a picture of. So this is not a general point of view of what happens here. So I take the polynomial. I don't know why, this is some psychological problem. I like my polynomial monic, but it's not really important, especially not in this model, where the coefficient, this sequence is IID, taking the values +1, -1 is probability half. Most of what I will say is valid in a much greater generality. Okay, so what do we know? So conjecture, which I attribute to Probabilistic and Poolen, although it's not exactly correct because they consider 0, 1, but let me ignore. So they will have 2 weeks to review this, right? So the conjecture is that F is irreducible asymptotically almost surely. Here H is fixed. Yeah, because the coefficients are ±1 and N goes to −1. So the conjecture is one that this is an actual conjecture that they did, that F is irreducible asymptotically almost surely. But if you are at it, why not the GF is Sn? I'm not sure that they wrote this. Again, only 2 weeks. They're busy writing letter of recommendation. I don't think I will have a problem. In fact, it's a funny story that I found this question in Math Overflow, and this is how I started working. So this is the conjecture. Let me tell you exactly, very briefly what is known. So firstly, we are in value they prove, well, maybe firstly, elementary, you can show that the probability that f is irreducible is at least 1 over n. This is just, you plug in 2, the number 2 in the polynomial, you get a random integer, it's prime with probability 1 over n because n is log of 2 to the n. And if it's irreducible, then almost surely the polynomial is irreducible. So 1 over n is easy by the prime number theorem. Konyagin, which was the best result, but also the method that he developed were used in all the results that were coming after. So this was 93. It's a funny story. It's the first paper of Punen. I heard that the stories that Udalitsko said, I found this brilliant undergrad in some project, and it was Punen. So. But I didn't ask Bjorn yet if it's true. So Konyagin, with analytical method, he proved that the probability that f is irreducible is at least a constant divided by log n. So this required a lot of analytical methods and very smart ideas. And then there was, so this was in, if I'm not mistaken, in 99. And then there was some results. Brouillard and Bariou showed that the general Riemann hypothesis implies that the lim of the probability that GF is irreducible is that f is irreducible is 1. Unconditional, I'm very shortening the story. Unconditionally, the best result is by myself with Koulopoulos and Cosma. So this is unconditionally, we get that the lim inf is positive. So this means that there is some constant which is very explicit. I think for plus minus, I mean, this work for general coefficients. So I think for plus minus 1, this constant is something like 1 over 1,000 or 10,000. I don't remember. I need to open the paper for this. But it's some constant that one can write down, which is bigger than that one. That the lim inf is positive, and very recently with Hocken, myself, Hocken, and Cosma, I mean, building on the result, I mean, developed before, we showed that the lim sup is 1. And I think Punen gave us some new ideas, so I think that it will be in the paper. So the lim sup is 1. But this result is specific to plus minus 1. The others are general, for general distributions. This is about answer 1. I told you what is the best known results, and I wanted to talk about question number 2 in this model. So number 2, we don't really, nobody can answer. Yeah, nobody can answer the question, but it's very interesting that the same group that make us solve the problem in the large box model is still the one that is difficult. So let me just, instead of giving exact names, so it's a series of papers by all kind of authors. We are Galois and myself with Koulopoulos and Kozma. We show that the same results is true when you replace irreducibility, but we cannot, none of us can distinguish between S and ON, but at least the group is one. I mean, this is under GRH. I mean, it's very similar to that story. It's the same condition, but let me not get into it. So here, in my eyes, the main challenge, if I write it in the most down-to-earth way, is you take the discriminant. This is something that I don't know how to solve. I take the discriminant of sum plus minus xi, and I ask what is the probability that it's a square, and show that this goes to 0. I mean, I'm very, let me see, baffled that when we cannot solve this. Because the discriminant look really like a random element module, some kind of symmetry. Of course, computer tell us that it's correct, but we don't know how to prove it. Specifically to plus minus 1, we can play with the two addicts to get some powers for which it's true. But if you break this symmetry, say take 0, 1, we don't do it. So this, which is funny to me, because although it's a completely different model and the actual formulation is different, still AN or square discriminant is the main difficulty to understand when this happens, because for some reason discriminant is complicated and we don't have good tools to actually estimate it. So yeah, so if you want to make me happy, please solve this. Finally, I gave you so many models, so let me talk about one more model. Let me talk about random polynomials over the p-adics. Okay? So, and I will be also very brief. I'm following Benjamin's suggestion. Thank you, Benjamin. I put many papers of all kinds of authors in the Discord. They will disappear in 2 weeks, but they remain in the archive. So you can read them if one of these subject interests you, and of course you can talk to me, I will be happy to. So here there is something interesting. First of all, if I choose F over the p-adics, so the most, I mean, the analog of the large box model in this setting is to take psi I distribute according to the Haar measure on ZP. This is what naively, this is the uniform, because it's such a nice group, then we really have the uniform. We don't need to take boxes larger, we just take the Haar measure. And here there is, here we are trying to, the statistics. I mean, polynomials over the p-adic do not tend to be necessarily reducible. They can factor in all kinds of ways with positive probabilities. So let me talk about the different statistic that is related, just because I don't have time. So you want to understand the probability, no, the average of the number of zeros of okay, and we have the names. So here there is a very And you know, this is a talk in algebra, but average is not really a good number. It doesn't tell us a lot. You know, the famous joke that a statistician drowned in a pool with average height of 10 centimeters, right? Because it's average, so you fell into. So average is not really the only thing that is interesting. We really want to know how this number distributes. So we need also distribution. Which one way to get it is higher moments. And Bar-Gava Ramona Fisher and Galois, I hope I pronounced the names correctly, in 21 prove or establish exact formulas for this. For those moments, and the nice thing is that they are universal, how do you call it? That they are rational function with the characteristic P. So universal, you call it? So they are rational functions. I mean, if you think about them as a formal function, about the formulas, all functions in the characteristic, they are rational functions in P. So you can kind of guess, and I will not have time to describe it, that there is a lot of motivic stuff hidden behind it. And when you consider things that are not uniform, that it's not our measure, you cannot expect all kinds of things like this. And the best, or maybe even the only known result is of Roy. '21 and 23 and 22. It's two papers. The first paper, he computed the average, but this was before the result of Bar-Gava, Cremona, Fisher, and Galois. And in the second paper, he computed all the moments, or up to some condition that I will not get into. But okay, let me write the statement. I'm not going to write a statement formally, but he computed moments for non-uniform polynomials. There are some conditions, but some technical conditions, but I find it a good result because it contains the plus minus one coefficient. Probability, this when you consider random polynomials, this is one of the go-to models. So if you can do something for this, this is a milestone, but it's a much more general result. And even the proof, at least for the second result, the higher moments is really some kind of universality of probability proof that he takes a general measure, and by some kind of arguments, he can reduce it to the Haar measure, so to the result of Cremona, Fisher, Bar-Gava, and Galois. I think that if you want to know more on this, I would suggest that you have one dinner, one night, and you can, if you compute Galois groups of Rubik cube one night, you can also talk about this. It's also interesting, I find. Yeah, and I just gave a brief overview. So this concludes my talk. Thank you so much.